Good morning, Bristol. I'm Dave Aronson, the T-Rex of Codosaurus, and I flew over here on my pterodactyl to teach you to kill mutants. But first, a few caveats. First, this talk is about the overarching concepts of mutation testing rather than using any particular set of tools. So there's not terribly much code in it. There's a little bit of code to test and then some tests and some supporting configuration. You could say it's low code. I know this is primarily a C and even more so C++ conference, and I do have a good bit of experience in C and a tiny bit in C++, but that was all a very long time ago. So what code there is in this presentation will actually be in Ruby, the main language I've been using for the past 13 years or so. If you don't like that it's in a different language, you can think of it as pseudocode, because Ruby is very close to just plain English. It reads very well. Not here to evangelize for Ruby, but confident you will understand it pretty easily. Also, I'd like to level set some expectations. This is listed on the agenda as an advanced talk. And that could be kind of sort of a little bit misleading, but to call it an introductory talk is even more misleading. What this is an introduction to an inherently advanced topic. So if you're already well-versed in mutation testing, I won't be too horribly offended if you go seek better learning opportunities at one of the other talks. But I'd still rather you stick around so you can correct my mistakes later, in private. And I mention mistakes because I do not consider myself an expert on mutation testing. But one of the dirty little secrets of public speaking, including at conferences, is that you don't need to be an expert on your topic. You just need to know a little bit more than the audience does, enough to make it worth their time to listen to you, and be able to convey it to them. And mutation testing is still so rare that most developers haven't even heard of it. So it makes a great topic for me. So let's start with the basics. What on infinite earths is mutation testing? In our universe, out of software development, not comic books, it's a software testing technique. Surprise! But why is this one different from all the others? You might look at the name and think, well, obviously, it's about testing the mutations used in genetic algorithms, right? Wrong. The big difference is that most other software testing techniques are about checking whether our code is correct. Mutation testing assumes that our code is correct, at least in the sense of passing its tests. And that in turn means that it assumes that we have tests. And I'll figure you probably know what happens when you assume, especially since I first learned that from Benny Hill. Anyway, mutation testing is instead about checking for two different qualities. One of them is about our production code, as you might expect, but the other is actually about our test suite. In my opinion, the more useful, interesting, and immediately helpful one is to check that our test suite is strict. Now, you may be thinking, but Dave, isn't that what code coverage is for? If we have 100% code coverage, doesn't that mean that all the code is fully tested? Long story short, no. Phil Nash mentioned in his talk earlier in this conference, in fact, right here on Wednesday afternoon, that test coverage is misleading because it shows lines of code, not data paths. And to expand on that a bit, the only thing that code coverage tells us is that some test executed those lines of code shown in green. It tells us nothing about whether the correctness of that code made any difference to whether the test passed or failed. By way of this illustration, let's look at some code. This is a possible test for the code on the previous slide. It's pretty straightforward once you realize what it's doing. It's calculating the next state of a cell in Conway's game of life. If you're not familiar with that, don't worry, we're not going to delve into it. I just want you to think about what happens if we do this and comment out the assertion. Our test still runs the function, but we're throwing away the result, not doing anything with it, not bothering to check it. And let's leave aside any quibbles about whether our testing tools should even let us get away with that. This may seem like an unrealistic thing to do, but let's have a show of hands. Who's at least seen assertions removed, commented out, and so forth? Oh, it's like most of the audience, at least in person, has seen them removed, presumably because tests were failing. And it's also easy to imagine scenarios where the assertions weren't even written in the first place because of all kinds of reasons, just forgot to, couldn't figure out how to obtain or check the results, or because the assertions weren't even necessary for the real goal, which was just to game the system and satisfy some pointy-haired manager's demand for high coverage. Test coverage is what I call a negative indicator. It's actually more useful in its absence than its presence. The code that isn't covered, we know for sure, is definitely not tested. That is a usable fact, and we can do something about it and go add tests. But what about the rest of it, the code that is shown as covered? Is it properly tested? We have no idea. Could be properly tested, poorly tested, or not tested at all. So how can we tell if the code shown as covered is indeed properly tested? In other words, whether the tests actually depend on the correctness of that code. That is where mutation testing comes in to get us back to the topic. To check that our test suite is strict, a mutation testing tool will find the gaps, excuse me, there we go, in our test suite that let our code get away with unintended behavior. Once we find gaps, we can improve our test suite by either adding more tests or expanding our existing tests to close the gaps. Lack of strictness usually comes from lack of tests, of course, or poorly written tests or poorly maintained tests, like ones that didn't keep pace with changes in the code. Speaking of which, the other thing mutation testing checks for is that our code is what I call meaningful, by which I mean that any tiny little change to the code should produce a noticeable effect on the behavior. Lack of meaningfulness, or meaning if you're into the whole brevity thing, comes mainly from code being unreachable or redundant or otherwise just not having any real effect. Once we find meaningless code, we can make it meaningful if that fits our intent, or just chop it out. Mutation testing puts these two together by checking that every possible, well, within reason, tiny little change to the code has a noticeable effect on the behavior of that code, and that our test suite is strict enough to notice that change and fail. Now, not all the tests have to fail, but every change should make at least one test fail. Now, that's the positive side, but there are some drawbacks. As Fred Brooks told us back in 1986, there's no silver bullet. Besides, those are for killing werewolves, not mutants. The first drawback is that it's rather hard labor on the CPU, and therefore usually rather slow. We won't want to mutation test our entire code base every time we save a file. Maybe over a lunch break for a smaller system, maybe a weekend or bank holiday for a larger system. But fortunately, most of the tools will let us check just specific files or classes, modules, functions, whatever, Plus, they usually include some kind of incremental mode, whereby we can test just what has changed since the last time the tool was run, or the last Git commit, or what's changed since the main Git branch, or some other such milestone. That sort of thing we can maybe do on each save for a fairly small system, if we remember to save early, save often, like we know we're supposed to, don't always do. Or at least over a shorter break than otherwise for the larger systems. Also, its CPU-intensive nature can also run up our bills on cloud systems such as AWS or Azure, however you pronounce it. Another drawback is that mutation testing is not at all a beginner-friendly technique. It tells us that some particular change to the code made no difference to the test results. But what does that mean? It takes a lot of interpretation to figure out what a mutant is trying to tell us. Their accent is very strange, and they're almost as incoherent as zombies, but with a much larger vocabulary, so they're not always on about brains. Even worse, sometimes it's a false alarm, because the mutation didn't make a test fail, but it didn't really make a difference in the first place. In all those cases, it can take still a lot of time and effort to figure out how. And even if a mutation does make a difference, there is quite a lot of code, usually in most systems, that we shouldn't even bother to test. For instance, if we have a debugging log trace that says the value of x is, and then the value of x, that constant string is probably going to get mutated, but we don't really care. We're certainly not going to bother covering that with a test. Fortunately, most of the tools provide some way to tell them, don't bother mutating this line, or perhaps this whole function, occasionally even files or classes, whatever. But that's usually done with comments, which can make the code a little less readable and clutter it up. Now that we've seen the pros and cons, how does mutation testing work, unlike this guy? It mutates copies of our code, hence the name. It does this to create test failures, otherwise known as faults. So mutation testing can be categorized as a fault-based testing technique. And this means it's related to something you might already be familiar with, Chaos Monkey from Netflix. Just like Chaos Monkey helps Netflix discover flaws in their error recovery, mutation testing helps us discover flaws in our tests and our code. But the way mutation testing does it is sort of upside down from what Chaos Monkey does. Chaos Monkey is best known for injecting faults into Netflix's production network. If all still goes well, in the sense that Netflix's customers don't notice and their metrics still look good, then Netflix knows that their error recovery is working fine. Mutation testing, however, injects changes, not necessarily faults. It doesn't know whether or not these changes will produce faults. We certainly hope they all will, but that's up to the test suite, and that's kind of the point of the whole thing. It injects them into copies of our code, not our actual network. And it does its work in our test environment, not production. And if everything still goes well, in the sense that our tests all still pass, that does not mean that all is well. It means that there is a problem. Remember, each change to our code should make at least one test fail. Mutation testing has also been compared to fuzzing, a security penetration technique involving throwing random data at an application. Mutation testing is somewhat like fuzzing our code rather than fuzzing the data. But it's generally, well, not only generally, but it's always not random. Most mutation engines will apply all the mutations that they know how to do. Some of the smarter ones will use the results from simpler mutations to know they don't need to bother with some more complex mutations or whole categories of mutations. But still, it's not random. But enough about differences. What exactly does mutation testing do and how? Let's start with a high-level view. First, ideally, our chosen tool breaks our code apart into pieces to test. Usually these are our functions, or methods if we're using an object-oriented language, but I'm just going to say functions. Some tools don't do this, but operate on a file-by-file basis, or maybe even the whole program. Both of these are far less efficient for reasons we'll see later. And from here on, I'll assume, though, that our tool is operating on a function-by-function basis. So then for each function, it tries to find the tests that cover that function. If the tool can't find any, either because there aren't any or we need to point them out to the tool, and we haven't done so, then most of them will just skip that function. And better yet, most of those will warn us about it, so we know we need to go point out which test covers which function or add some tests, whatever. But some will use the whole test suite, which is horribly inefficient because it's running a lot of tests that it doesn't need to run in order to check that function. So assuming we're not going to skip this particular function, next the tool makes the mutants. And to do this, it looks closely at the function to see how it can be changed. And for each way that it could change that function, the tool will make one mutant with just that one little change to it. And once our tool is done making all the mutants it can from this function, it iterates over the list. And now we get to the heart of the concept. This chart represents the progress of our tool. As far as I know, none of the tools give us anywhere near so complete a report, let alone in such a nice, neat format. But this is a conceptual model that I use to illustrate how it works. So for each mutant made from a given function, the tool runs the function's tests, but it runs them with the current mutant instead of the original function. If any test fails, in the standard industry terminology, this is known by the unfortunate term of killing the mutant. And here I'm going to take a slight detour because some people object to the violent communication of this metaphor, especially since in the comic books, mutants are often metaphors for marginalized groups of people, and the tech industry is finally becoming more sensitive to such issues. So I'm trying to come up with some nicer terminology, and I'm leaning towards terms like rescuing or perhaps covering the mutant. This makes sense if you think about what happens in the normal course of testing. In the normal use of test coverage, normal code should be covered by at least one test, and it should let all tests pass. By way of analogy, in mutation testing, mutants should be covered, at least in my new terminology, by at least one failing test. Remember, each change should make at least one test fail. I'm going through all this motion to try and drill it into your head so you remember that big takeaway. Unfortunately, the term covered is already in use, meaning something essentially the same as in normal test coverage, just that the mutant has been run by at least one test. So I'd like to replace that with saying that the mutant is exercised or possibly inspected or checked. But it's a long, hard uphill battle trying to change terminology that people are already using. Oh well. Anyway, whatever we call it, when a mutant makes a test fail, and for the rest of the presentation, I'm going to stick to industry standard terminology of killing it. each mutant should make at least one test fail. So when it does, that's a good thing. It means that our code is meaningful enough that the tiny change that the tool made to create the mutant did have a noticeable effect, and that our test suite is strict enough that at least one test noticed that change and failed. Then the tool will mark that mutant as killed and stop running any more tests against it and move along to the next one. Once a mutant has made one test fail, we don't care how many more it could make fail, like perhaps some of tests 6 through 10 for mutant number 1. Like so much in computers, we only care about ones and zeros. On the other claw, if a mutant lets all the tests pass, then the mutant is said to have survived. And that means it has the superpower of mimicry, skilled enough to fool our tests. This usually means that our code is meaningless, or our tests are lax, or both. And now it's up to us to figure out how. Now let's peel back one layer of the onion and look at some technical details of how this works. First, our tool parses our code usually into an abstract syntax tree. There are some tools that work differently, like working on bytecode, and some, mostly proofs of concept, even work on the raw written source code. But the vast majority of tools that are considered ready for prime time use an AST. So let's just roll with that. And I know those boxes are too small for most of you to read easily, but we don't need to examine this one in detail. And a brief refresher in case any of you haven't dealt with an AST lately. It's a tree structure that represents the semantic meaning of our code. The leaves are usually values like a variable, literal, constant, or whatever, and the other nodes are things like function calls and operations and their operands and layers of structure like while loops and ifs and functions and modules and such. So I'll just go through all that. Anybody need any more of a refresher on ASTs? Okay, cool. After our mutation testing tool creates an AST out of our code, then it traverses that tree looking for subtrees or branches, if you will, that represent our functions. After finding them, it handles them pretty much as I said before, starting with looking for each one's tests. But how does it do that? That usually relies mainly on us developers either annotating our tests or following some kind of naming convention for the tests and sometimes the functions in the files or both. These manual techniques are often supplemented and sometimes even replaced by having the tool look at what tests call what functions. This gets a little tricky when the function is not called directly from the test. You can assume that foo test helper calls foo and makes some assertions about it. After the tool has found the functions tests, and assuming it won't skip this function because it didn't find any, then it makes the mutants. To make mutants from an AST subtree, it traverses that subtree just like it did to the whole thing. However, now, instead of looking for smaller subtrees it can extract, twigs or something, I guess, it looks for nodes where it can change something. And each time it finds one, then for each way it can change that node, it makes a copy of the entire AST subtree that represents that function, with that one node changed in that one way. For instance, suppose our tool has started traversing the AST I showed earlier and has only gotten down to this while loop. For each way that it can change that one node, it will make a fresh copy with that one node changed in that one way. That everything else in the subtree will remain the same. After it's done making as many mutants as it can from that node, it'll move on to the first child of that node and try and make a bunch of mutants from that node, and so on until it has traversed the entire subtree. Now I've been talking a lot about changing things and mutating nodes and whatnot. So what kind of changes or mutations are we talking about? There are quite a lot. It could change a mathematical, logical, or bitwise operator from one to another. In languages and situations where we can do so, it could even substitute one from a different category. So for instance, in many languages, we could treat anything as Booleans, and in particular in C, we don't have real Booleans per se, but we can treat anything as them. So x times y could become, for instance, x and y, or x exclusive or y. But remember, some tools will only make one change per node. So for instance, a plus might only be changed to a minus. While with other tools, it could be mutated into any of those and a lot more. That will find a lot more possible errors. When the order of operations matters, such as with subtraction, division, exponentiation, or string concatenation, it could swap them. It could change a comparison from one to another. Again, some tools only make one change per node. So for instance, less than would be only mutated into greater than, or possibly less than or equal. While with other tools, it might be mutated into any other comparison, including equals or not equals. I think you get that concept by now, so I'm not going to repeat that more. But there is another wrinkle. Some tools work on a principle of never doing semantic addition, meaning they will never make something more complicated, only just as complicated or perhaps less. So some of those tools will never change, for instance, a greater than into a greater than or equal, because semantically, greater than or equal is a more complex expression, even though it's a single operand in most languages and even most CPU architectures these days. Just breaking it down to its abstract logical meaning, it's more complicated. So such a tool would only turn a greater than into a less than, or possibly an equal, but not a less than or greater than or equal. Okay. It could insert or remove a logical or mathematical or bitwise negation. It could remove entire lines of code, though usually because it's a statement rather than looking at the physical written lines of source code. Though, as I said earlier, some tools do operate on that basis. It can remove a condition so that something that might either be done or skipped will always be done. It can remove a loop control so that something that might be skipped, done once, or done many times is done exactly once. It could theoretically, but very few do, scramble or truncate argument lists of function calls. Truncation will often result in a syntax error from having the wrong number of arguments. And in the interests of just not doing anything that would result in a trivial case, like raising an error condition, a lot of them will skip that. However, if our language allows for default or variadic arguments like C does, and many modern languages do, this could be perfectly fine. And it could do likewise to function declarations. And this will usually result in a syntax error where it's called from for having too many arguments, or inside the function from having an unknown variable. But again, if we have default or variadic arguments, this could be okay, and it can help reveal times when we are shadowing a variable from an outside scope. That's just a little extra gravy. It's not one of the main points of mutation testing, but just something else helpful. Of course, any decent compiler or interpreter should warn us when we're shadowing, but we don't always have the best tools, nor crank up the warnings and pay attention to them. That's one of my favorite techniques for improving inherited code. And moving on, it could replace a function's entire contents with returning a constant or any of the arguments or raising a deliberate error or nothing at all if the language in question permits. There's even a style of mutation testing called extreme mutation testing that only uses complete removal of function bodies. This results in a lot fewer mutants to test, so it's a lot faster. But of course, there are a lot of kinds of problems that won't detect. But it makes a great first pass to be followed up later with more thorough testing. And it could add things to, remove things from, or completely empty out collections like lists, tuples, maps, vectors, and so on. And of course, it could mutate each item in such collections. It could change a constant or variable or function call to some other value. It could even change it to something of a completely different and incompatible type if that's not a syntax error in the language in question, such as changing a number into, if I may quote Smeagol, string or nothing. There are many more, but once again, I trust you get the idea by now. From here on, there are no more low-level details I want to add, but that means we finally have the opportunity to walk through some examples. So we'll start with an easy one. Suppose we have a function like this. Yes, it's a very contrived example. The only excuse I could think of is maybe you're working in an extreme polyglot application. Some languages use the double star, some use a caret to denote exponentiation. So you just write a wrapper so you don't have to remember which one is used by the language you're working in this hour. Think about what a mutant made from this might return, since that's what our tests would be looking at, because this doesn't have any side effects. Mainly, it could return results such as any of these values and many, many more, but I had to stop somewhere. Now, suppose we had only one test, like this. This is a rather poor test, and I think it's clear to most of you why. We'll see in very much detail shortly. But even so, most of these mutants would still get killed by this test, the ones shown here in crossed out green. The ones returning constants are very unlikely to match. There's no particular reason our testing tool would be putting a 4 there, as opposed to 0, 1, or other such generally significant numbers. Subtracting gets us 0, dividing gets us 1, returning either argument alone gets us 2, and even the ones raising a deliberate error condition will at least make the test not pass. But addition, multiplication, and exponentiation in the reverse order all still get us the correct answer. Mutants based on any of those mutations will therefore survive our test. So how do we see that actually happening? When we run our tool, it gives us a report that looks roughly like this. The exact words and format and amount of context and so on will vary greatly, depending upon exactly which tool we're using for which language and so forth. But the information should be pretty much the same. The minus and plus signs are for removals and additions. I trust you've seen something similar to that at least. To fully unpack this, what it means is that if we changed the function called power, which is in file demo.rb starting at line 42, in any of 4 different ways, then all of its tests would still pass. And then it goes on to tell us that those 4 ways are to change line 42 to swap the arguments, to change line 43 to change the exponentiation into either addition or multiplication, or to change line 43 to swap the operands of the exponentiation. So what is this set of surviving mutants trying to tell us? The very high-level message is that our test suite is not sufficient, either because there aren't enough tests, or the ones we have just aren't very good, or both, but we knew that. The question boils down to, how are these mutants surviving? Are they pulling heists? Are they living at the Xavier Institute, or what? The usual answer is that they give the same result as the original function, either returning it, or if we're not doing pure functional programming, it has the same side effect, whatever it is that our tests are looking at. To determine how that happens, it helps to take a closer look at one mutant along with a test it passes. So let's start with the plus mutant. Looking at that change together with our so far one and only test makes it much clearer that this one survives because 2 plus 2 equals to 2 the 2, and so does 2 times 2, but he's in the background. We can save him for later. So how can we kill this mutant? In other words, make it return a different answer than the original function, given some set of inputs. There's the key. What's our set of inputs? It's quite simple in this case. We have to just use arguments such that x to the y is different from x plus y. For instance, we could add a test or change our existing test to something like this, to assert that 2 to the 4th power is 16. All the mutants that the original test killed, this would still kill. But also, 2 plus 4 is 6, not 16. So this should kill the plus mutant just fine. And while we're at it, 2 times 4 is 8. You know, we programmers, especially C and C++ programmers, should know our powers of 2 really well. And that's also not 16. So this will also kill the times mutant. However, the pair of argument swapping mutants still survive. How can that be? It's because 2 to the 4th power and 4 to the 2nd power are both 16. Since the function deals with powers, it probably would have been smarter to avoid argument pairs where one is a power of the other. Oops. But anyway, we can attack the argument swapping mutants separately. No need to kill all the mutants at once and be some kind of superhero about it. To do that, again, we can either add a test or adjust our existing test to something like this, to assert that 2 to the 3rd power is 8. 3 squared is 9, not 8. So this kills the argument swapping mutants just fine. 2 plus 3 is 5, and 2 times 3 is 6, and both of those are, guess what? Not 8. So the plus and times mutants stay dead, and we don't get any zombie mutants wandering around. With these inputs, the correct operation is the only simple common operation that yields the correct answer. This isn't the only solution, though. We could have used 2 to the 5th, 3 squared, 3 to the 5th, vice versa, many, many more. There are lots of ways to skin that flurkin. This may make mutation testing sound simple, but this was a downright trivial example, so it was easy to think up arguments that would make all mutants, within reason, behave differently from the original function. So let's look at a more complex example. Suppose we have a function to send a message, like so. This function send message uses a loop to call send bytes over and over, picking up where it left off until the message is all sent. This is very common in communication software, and this being a C and C++ conference, I'd bet a lot more of you have done something very similar to this than when I go to something like a Ruby or JavaScript conference. Now, a mutation testing tool could make lots and lots of mutants out of this, but one of particular interest is this, removing those lines with the minuses. This is an example of removing a loop control. And that would make it effectively read like this. Now, suppose that this mutant does indeed survive our test suite, which consists mainly of this. There's a bit more that I'm not going to show you quite yet, dealing with setting the size and creating the message. But even without seeing that test code, what does the survival of our non-looping mutant tell us? If a mutant that only goes through this while loop once acts the same as the original code, as far as our tests can tell, then it means our tests are only making our code go through that while loop once. So what does that mean? You'll find that interpreting mutants involves a lot of asking yourself, so what does that mean? Often recursively, sometimes so recursively your stack may be in danger. I think humans could use some tail call optimization. In this case, it simply means we're not testing with a large enough message to make it go through that loop twice or more. And the biggest cause of that is just we're using a fairly small message by comparison. For instance, and here comes the previously hidden code. Suppose our maximum chunk size, what send bytes could handle in one shot, is 10,000 bytes, but for whatever reason, we're only testing with an itty-bitty little 3-byte message, or 4 if we have a null terminator. There we go. The obvious fix is to use a larger message, larger than the maximum chunk size, and it's very easy to construct one. Just take the size, add one, make something that big. But perhaps, to paraphrase Shakespeare, the fault, dear Bristol, is not in our tests, but in our code that these mutants are survivors. Perhaps we did test with the largest permissible message out of a set of predefined messages, or at least message sizes. For instance, here we have small and large message sizes, and we test with a large, and yet our mutant survives. What is this mutant trying to tell us now? In this case, it's trying to tell us that a version of send message with the looping removed, as happened in that mutant, will do the job just fine. If we remove the loop control, we wind up with this code I showed earlier. And if we rerun our mutation testing tool, it'll show a lot of other stuff as now being redundant because we only needed it in order to support the looping. And if we basically lather, rinse, repeat, we wind up with something like this. And now it's pretty clear that the ultimate message is that the send message function may well be entirely redundant, and we can just use send bytes directly. Now, I say it may well be redundant, not it is redundant, because in real world code, there may be some logging or error handling and whatnot needed in send message, but at the very least, the looping was redundant. Fortunately, when it's this kind of problem with code that's either dead or unreachable or redundant, the solution is clear and easy. Just remove whatever it is that the mutant didn't have. And this will also make our code more maintainable by getting rid of useless cruft. Now that we've seen a few different examples of spotting bad tests and redundant code, some of you might do better staring at code than hearing me blather on and on about it. So here's some even higher level pseudocode, giving you the general outline of how it works. I'll pause a moment if you want to take pictures. nobody's whipping out a camera, so I will just proceed. Those of you online, I guess you can take a screenshot or something. So next up, I'd like to answer some occasionally asked questions. Mutation testing is still rare enough that I don't think there are any really frequently asked questions. First, this all sounds pretty weird, deliberately making tests fail in order to prove that the code succeeded. Where did this whole bizarro idea come from anyway? Mutation testing has a surprisingly long history, at least in the context of computers. It was first proposed in 1971 in Richard Lipton's term paper at Carnegie Mellon University titled Fault Diagnosis of Computer Programs. The first tool didn't even appear until 9 years after that, in 1980 as part of Timothy Budd's PhD work at Yale. Even so, it was still not practical for most people with consumer-grade machines until perhaps the last couple of decades, with advances in CPU speed, multi-core CPUs, larger and cheaper memory, and so forth. And that leads us to the next question. Why is it so CPU intensive? To answer that, we need to do some math, but don't worry, it's pretty basic. Suppose our functions have, on average, about 10 lines each, and each line has about 5 places where it can be mutated to any of about 20 alternatives. That works out to about 1,000 mutants per function. And for each one, we'll have to run anywhere from one of its tests, if we kill it on the first shot, to all of that function's tests, if we kill it on the last shot, or worse yet, it survives, gets away. Suppose we wind up running just 1/10 of our tests for each mutant. Since we start with 1,000 mutants, that's still about 100 times the normal amount of test runs. So if our test suite normally takes just a zippy 10 seconds, mutation testing with these assumptions and ignoring variable overhead and such will take about 1,000 seconds. And that might not sound like much because I'm saying seconds, but if you do the math, that's almost 17 minutes. I don't know about you, but I don't like sitting there waiting 17 minutes for some test results. But there is some good news. Over the past decade or so, there's been a lot of research on trimming down the mutant horde, mainly by weeding out those that are equivalent to the original code or redundant with other mutants or trivial in other ways, such as raising an obvious error condition. And such things have reduced the number of mutants per function on average by about 2/3. But even with that rare level of success, it's still no silver bullet because that takes a lot of CPU time itself. And the remaining number of mutants is still usually rather large. The next common question is, when making each mutant, why change it in only one way? Oops, there we go. There are, in fact, multiple reasons. First, the main theoretical underpinning of mutation testing is the competent programmer hypothesis. So let's give that a quick check. Raise your hand if you're competent. Okay, almost everybody. The rest of you, you probably really are competent, so maybe go read up on imposter syndrome. But it's still enough to confirm the hypothesis. So what is the competent programmer hypothesis? Basically, it's the idea that we usually have a pretty good clue what we're doing most of the time. And when we make a mistake, it's usually just one small mistake, like a typo or adding when we should have subtracted or getting some arguments backwards or something. Now, does that sound at all familiar, that sort of small little mistake? It's exactly the kind of substitution that a mutation testing tool will make. So you can sort of kind of think of mutation testing as a did you mean kind of function. And if it can't tell the difference between some other operation and what you actually wrote, yeah, there's a fairly good chance that it's a bug. Another reason is that it helps us poor humans focus. It's much easier to tell what a mutant is trying to tell us if we're only talking about one thing in the first place. Just a moment. You can think of it sort of like using the single responsibility principle. Another reason is that multiple changes may balance each other out, leading to more false alarms. For instance, remember that first trivial example and its argument swapping mutants. If one mutant had both of those mutations, the first would swap the arguments and the other would swap them right back for no net effect. Another trivial example would be if one mutation incremented something and another decremented it right back to the original value. But mainly, allowing multiple mutations would create a combinatorial explosion of mutants with orders of magnitude more mutants per function, which would make it even more CPU intensive. I'll spare you the math, but with our earlier assumptions about code size and trimming down the mutants and everything, with one mutant per function, we'd have about 333 mutants per function, and a third, but I'm rounding. With two, we'd already have almost 110,000, and with three, we'd have over 35 million mutants per function. Never mind actually running the tests, just creating the mutants would get to be quite a heavy workload. But we can avoid this huge workload and the increased false alarms and the lack of focus if we just limit it to one mutation per mutant. The next question is, it sounds like mutation testing just helps us make sure that our test suite as a whole is strict. Can it help us assess the quality of an individual test? Yeah, there is a way theoretically, but it would take a lot longer. You may remember how I said early on that when a mutant makes a test fail, the tool will mark that mutant killed and stop running any more tests against it and go on to the next one. So when we're done with a given function, we wind up with a chart kind of like this. Again, let me remind you, as far as I know, no tool actually gives us a chart like this. But if we were to have access to all the information, it would be conceptually like that. Now, if we were to actually run the rest of the tests against all those mutants, that would take longer, but it would give us a more complete chart like this. And we can use this chart to assess the quality of at least some individual tests. So look at tests 4 and 9. None of the mutants make either of those tests fail. Now, this isn't an absolute indication that they're bad, but it does imply that they might merit a closer look. You can think of it like a code smell. And you could also take this concept a little further and look at the tests that only stop one mutant and those that only stop two. But I think you'd quickly reach a point of diminishing returns, probably at 1. And lastly, as I mentioned earlier, mutation testing assumes that we have tests already. What if we don't? Can mutation testing be of any help in that case? Well, first of all, whoever wrote a significant code base of production code with no tests needs some educating, like with a 2x4, about the value of tests. But yes, mutation testing can help you build your test suite in the first place. You can start with a meaningless test and run your mutation testing tool. You'll probably get a lot of mutants, many of them being duplicates, telling us about essentially the same problem. Out of the mutants for each function, just pick one. You can pick it randomly, no need to overthink it. Try to kill it by adding a test. This will probably kill many of the others as well. Then lather, rinse, repeat, though on further iterations you might wind up improving a test rather than adding a test. This won't guarantee that you wind up with a really good test suite, but it's a good start. And a lot of code will probably remain untested, if not in statement, then at least in semantics. But you can use it as a starting point. To summarize at last, mutation testing is a powerful technique to ensure that our code is meaningful and our tests are strict. It's easy to get started with in terms of setting up most of the tools and annotating our tests if need be, which may be rather tedious, but at least it's easy. But it's not so not so easy to interpret the results, nor is it easy on the CPU. And even if these drawbacks mean it's not really a good fit for our particular projects at the moment, I still think it's just a really cool idea in a geeky kind of way. If you'd like to try mutation testing for yourself, here's a list of tools for many popular languages and platforms and some other ones. I doubt many of you are doing Fortran 77 these days. In particular, for plain old C, we have mutate.py. Yes, it's written in Python, but it's for mutating C code. And Surceror, however you pronounce that. For C and C++, we've got ACMUT, DexTool, Mart, CPP, Mutate++, Mutate, CPP, and again, Surceror. Just in alphabetical order. Nothing else implied there. I have not tried all of those. Okay, I haven't tried any of those. And for anything using the LLVM toolchain, you can also use LLVM mutate and mul. At this point, I usually ask if everybody's done taking pictures, but I don't see any cameras out in the first place. Okay. Before we get to Q&A, I'd like to give a shout out to TopTal, a consulting network I'm in that has a speakers network that helped me prepare and practice previous versions of this presentation. Please use that referral link if you want to hire us or join us. And that's also where that QR code goes. And many thanks to Marcus Sherp, who created Mutant, the main mutation testing tool I've actually used. It's for Ruby, sorry, not C or C++. And he's been very willing to answer my ignorant questions and critique the original version of this presentation. And now it's your turn. If you have any questions, I'll take them in just a moment. If you think of anything later, there's my contact information. Okay. Do any tools simply add (1) or (true) to argument lists? I have not seen that specifically done. I suppose theoretically they could, but again, they generally operate on a theory of semantic limitation. That is, either keeping it about as complex as it was or simplifying it rather than adding anything. So I would be a little bit surprised to see that, but it is, of course, theoretically possible. And next we have, oh, by the way, that question was from Matthew. Now Francois asks, is there a way to select which kind of mutations the tool is applying? For example, if I have a mathematical function taking some double type arguments, I can't get any good information if my mutated test survived by swapping arguments, so I don't want this kind of mutations. Yes, I have heard of, but not personally used, ones where you can basically select which precise types of mutations it will do, sometimes by broad categories, sometimes by individual things. In the theoretical treatments of mutation testing in general, there are a lot of these mutators that have very specific names, usually a 3-letter acronym, and they often have configuration files where you can say this one yes, this one no, or true, false, 1, 0, whatever. And some of them will group them, so just don't do any of this group. In all kinds of ways you can configure some of them. Others, not so much. Next, Matthew asks, TDD should guarantee we have a quote-unquote good test for every line of code. How does code with lots of TDD sit with mutant testing? Okay, TDD is, in my opinion, a really good thing, but it is, as Fred Brooks would say, no silver bullet. It guarantees that we have, well, if we follow it strictly, a test for every line of code, but again, that does not mean that we have tested all the semantics of that line of code. It has more or less the same flaw as most testing based on what humans think up, which is that we don't think of everything. So it's quite common to see, as one of the keynoters, I think, pointed out, error paths and such not very well tested. You may have a test that tests whether or not it raises the error in a particular situation, but did you test that it raises that precise kind of error, or that it just raises an error at all? There's all kinds of ways that a mutation testing tool will tweak your code and come up with situations that you just didn't think of. Okay, the question is, has any work been done on what types of mutations are more productive than others? I believe there has been. I have not delved deep into the academic research on this sort of thing. Frankly, the academic papers tend to put me to sleep. But I have been on the sidelines of some discussion about such things, and I don't remember the exact result, but yes, there were some groupings that were more productive than others. I would imagine that the mathematical operator substitutions would be particularly productive. That's often tricky stuff to get quite right, whereas things like string concatenation or wrong number of arguments, that's probably much less likely to catch something we've done wrong.
As a practical industry sort of report, I am not responsible for mutation testing where I work. We have that turned on as a relatively common optional feature. The class of things that is enabled most frequently is inverting conditionals. If statements, control structures for while loops, if you invert the meaning on the conditional and that triggers, those are a fertile ground for you have semantic missing coverage. That seems to be the only thing that I actually see in practice at scale.
Okay, I'm actually a little surprised that a complete inversion would be quite so fertile. You'd think that decent testing would take care of that, but the boundary conditions less than versus less than or equal to, that would be quite fertile, I think.
I'm surprised as well, but I have to assume that the people that are, curating the defaults have done some of the research. So I don't know, but that's what I see.
Yeah, so a lot of the tool authors do seem to be heavily into the academic research, and I would not be the least bit surprised if some of them had done a lot of research on exactly which mutations were most productive and curated the defaults. Good idea. Yes.
Thank you for the talk. I just wondered if there are any other testing techniques where mutation testing would be a good complement. So I'm thinking of things like property-based testing or things like that.
Yes, I've occasionally heard of it being paired up with property-based testing. It is somewhat similar. I recall I referenced fuzzing earlier. It is very closely related to property testing. I've been meaning to actually delve into property testing myself. Haven't had the time yet. Oh well. Other than that, I've heard of a lot of people using it with TDD. I suppose you could extend that and use both of those along with BDD, which I consider basically just a high-level form of TDD. And other weird testing tricks, I don't know, but I've been toying with the idea of putting together a talk on all kinds of testing techniques that devs could benefit from but have probably never heard of, like property testing and mutation testing and so on.